Good afternoon and welcome to the HamSCI Telecon. I am very happy to be here, and I'm very happy to welcome Tom McDermott N5EG, who very nicely responded to my call for presenters, and he offered to give us a presentation today on power over Ethernet. Now, this is not normally a topic that is specifically HamSCI related, but Tom is a full voting member of the IEEE specification, and he's a very good engineer, so I thought we would find his talk very interesting. Also, maybe there's some potential future application to the personal space weather station design. So we'll hear from Tom, and then after Tom, we'll have open discussion. And I'm going to propose that for the next bi-weekly telecon, which is not, of course, next week, but the week after, that maybe we do a review of data from the Tonga event, because I know there's been a lot of discussion on the listserv about that. So maybe we can see what people have a general discussion about that. Maybe people will have some presentations they want to share. Sound good? Great. Well, with that, I would like to welcome Tom McDermott N5EG, and he's going to talk to us about power over Ethernet.
Okay, can you see the slides, Nathaniel?
Yes, but you're a little quiet.
Okay, let me try that. That's a little closer to the mic. Is that better?
That is better.
Okay.
But we're hearing the room. They're not hearing your mic.
Well, let's see. Let me check. Let me stop sharing for a second and make sure I've got the right mic selected.
There's also a Zoom setting to minimize that. It's down in the audio settings, advanced.
Okay, where would I'm going to have to hunt through audio settings. Okay. Audio settings, and it says I'm picking the right microphone, and it's on automatic mic adjust. Okay, this is manual mic adjust. Is this any better?
That is louder.
Okay.
There is a background and filter setting as well.
All right. Let me see if I've got that on my background. Suppress background noise is auto. Now it's on medium. Is that any better? Okay. And this is high on suppress background noise.
Really doesn't make a big difference, but we can understand you.
Okay. Okay, so Nathaniel said, I used to be a voting member of 802.3 Ethernet Working Group. And when I retired, I also retired from that, as it's pretty expensive to maintain your voting membership. And so, so I just follow along with what's going on now. So power over Ethernet, there's quite a long list of things you can do with it. Some of the common applications are voice over IP telephone, where the telephone set has a single Cat5 or Cat5e cable, and both the data from and to the telephone and the power to the telephone go over a single cable. I've used it for point, tilt, zoom, conference room cameras, high quality video cameras, wired security cameras. A common one is outdoor roof and tower mounted microwave data radios, where you don't want to run a long feed line up to the radio because of the loss of microwave. So instead you send power up to the radio over Ethernet, and then data up to and back down from the radio over the same Ethernet, and you can power the radio over Ethernet. For example, the amateur radio Arden equipment commonly uses power over Ethernet. Of course, Wi-Fi access points are commonly powered over Ethernet. Increasingly, there are small switches and routers which have power over Ethernet inputs. So you can locate a small switch in a closet with no power and have it actually switch multiple Ethernet instances. Intercoms, IPTV decoders, wall clocks, control systems, intelligent lighting controllers, point of sale. There's another interesting one, inline Ethernet extenders, where if you have to reach over 100 meters on Ethernet, you can locate a repeater out in the middle of a cable and power it from one side using power over Ethernet and use it as an active repeater to extend the circuit. The history, before 2003, there were proprietary voice over IP phones and some wireless access devices that were powered over Ethernet cable. I think these were primarily Cisco. The phones, I'm pretty sure were. I don't know about the other devices, but I recall Cisco having most of the devices. In 2003, the IEEE standardized 802.3AF called Power over Ethernet, and it defines the polarity, the voltage, safety mechanisms, signaling for the amount of power, the various injection modes for about a 13 watt source. And based upon that standard, chip suppliers designed and started producing ICs for the power sourcing equipment. That's what sources power onto the Ethernet cable, and for the powered device. That's what receives power from the Ethernet cable. And so a little bit after 2003, equipment manufacturers started to migrate over to the standard version of power over Ethernet. And it was really important to standardize that because it meant that phones and power over Ethernet injectors and switches were intermatable in a standard way. One of the standards, one of the pre-standard versions used the opposite polarity, for example, which was a difficult thing to try to be compatible with. In 2009 and then in 2016, in 2009, Power over Ethernet Plus was standardized. And in 2016, Power over Ethernet Plus Plus was standardized. And we'll talk about those in a second. Many of the older Ubiquity devices use 24 volt proprietary Power over Ethernet. So these are like the Ubiquity 2 gigahertz and 5 gigahertz radios that folks use. And so they don't quite interoperate with standard. It appears, as far as I can tell, that Ubiquity is kind of migrating their products over to the 802.3 PoE plus and plus plus standards. So hopefully the days of proprietary PoE will be pretty much drawn to a close pretty soon. There are three types of PoE. 802.3AF-2003, which in this presentation I nicknamed PoE, uses two pairs in the cable to provide about 13 watts of power to the load. 802.3AT-2009, or PoE Plus, uses two pairs for power, and it's capable of providing about 26 watts of power to the load. And then 802.3BT 2016, which is nicknamed PoE Plus Plus, uses four pairs of the Cat5, Cat6 cable, and it can provide between about 51 and 71 watts of power to the load device. So there are two different injection modes for power over Ethernet. There's mode A, which is typically end span injection. And that's where the switch injects power onto the data pairs. And the reason that it's used in the end span is because in the end device, you have access to the sending transformer center taps. Mode B is typically mid-span injection, and there you might put a separate injector module in the middle of the cable. It usually injects power onto the unused pairs. In 10 and 100 meg Ethernet, one pair is used for transmit, one pair is used for receive, and there's two unused pair. In the mid-span injector, typically we'll use those unused pair to provide power to the device. In the mid-span, you don't have access to the center tap of the transformers, and so that's why typically you use a separate injector module. So this diagram, which comes from Microsemi, shows the two modes. The green is mode A, and the red is mode B. It's not the polarity, it's the mode. So you can see using the green wires, you inject plus 48 volts into the center tap of the 1-2 pair, and the 48 volt return comes from the center tap of the 3-6 pair. And then the load device on the right side, the powered device, extracts 48 volt power from the center taps of the active transmit and receive data pair. Transmit in this case refers to transmit from the end station on the right to the switch up on the left. And so the alternate mode is to use the unused data pair, and that's shown in red here, where the power sourcing equipment will put 48 volts onto the 4-5 data pair, and the return for the 48 volts comes back on the 7-8 data pair. So you can see for midspan injection, if you want to power using mode A, the green wires, you would have to place a transformer into the injector so that you would then have access to the center tap on the transmit and receive pairs. If you instead used mode B, or the red lines, you could build an injector that didn't have the additional transformers in it, and you could just connect the wires through on the transmit and receive pairs. And so early on, the green was typically the end span injector, and the red was the midspan injector. When we go to gigabit Ethernet, all 4 pairs are used in gigabit Ethernet. The data is actually sent across all 4 pairs in transmit and in receive. So the pairs are full duplex. There's 250 megabits each direction on each pair. And so in order to inject power here again, you could use mode A, which would be the green wires on the 1-2 and 3-6 pairs for send and return, or you could send the power on the 4-5 and 7-8 center taps. So typically at gigabit Ethernet, you use Cat5e cable, you can use Cat6. The reason being is that because you're transmitting on all 4 pairs and receiving on all 4 pairs, you have issues with crosstalk between the pairs. And so Cat5e is designed to have lower crosstalk between pairs on the ends. Now in PoE and PoE plus, you use either the green or the red. In PoE plus, it's called 4-pair power over Ethernet. You essentially use the red and the green to send power. So you'll source plus 48 volts on 2 of the pairs, and you'll get 48 volt return on the other 2 pairs. And that, of course, means that you can pretty much double the amount of power that you can send down the cable to the load device. So in midspan injection, for a gigabit, you have to have transformers because you have to have access to the center taps on all of the devices. And so if you use the green for PoE plus, or you can use the red for PoE plus. And for PoE plus, you use generally the red and the green. So the powered device generally sums the power from the 1-2 and the 4-5 pair for plus, and it uses 7-8 and 3-6 for return. And that way the powered device doesn't really care how the power was injected onto the pairs. It just essentially diode ores together the appropriate 48 volt plus and the 48 volt returns, so that no matter how you inject it in any of the cases, it'll be able to pick up power. Ethernet uses at one time, I think, 1,000 volt isolated transformers, although I think a recent addendum may have increased the isolation voltage on the transformers. So typically the powered device will use a DC isolated switching converter to convert the 48 volt that it receives to the 5 volt or 12 volt or whatever voltage is needed by the load device, while maintaining galvanic isolation. So typically Ethernet is galvanically isolated, and in power over Ethernet, most devices will maintain that by using isolated switching converters. So in power over Ethernet plus, they use 4 pairs. Essentially, it's the green, which is mode A, plus red, mode B, of the previous 1 gig N-span and mid-span figures. So if we look at the power parameters, type 1 is the original power over Ethernet. Power over Ethernet plus is called type 2, and then power over Ethernet can be type 3 or type 4. The power at the powered device minimum guaranteed for type 1 is 12.95 watts. For type 2, it's 25.5 watts. For type 3, it's 51 watts. And for type 4, it's 71 watts. And so you can see if you have a type 4 PoE, you can deliver a fairly substantial amount of power to the load device. This gets to be interesting for a lot of different applications. For type 1, the voltage at the power sourcing equipment is a minimum of 44 volts and a maximum of 57. And you can see for types 2, 3, and 4, the minimum allowed voltage at the PSE climbs a bit in order that you can send more current down the cable and not have a low voltage condition at the load. The voltage at the powered device is a minimum guaranteed 37 volts for type 1, 42.5 for type 2 and 3, and 41 for type 4. In type 1 PoE, you can send a maximum of 350 milliamps over the pair. For PoE plus, a maximum of 600 milliamp over the 2 pairs that you use. One pair is 600 milliamps one way, the other pair is 600 milliamp return. And for PoE plus, it's 600 milliamp per pair as well. For type 4, you can go up to 960 milliamp per pair. So type 3, since it uses 4 pair, gets you essentially the ability to source 1.2 amps of current to the powered device. And type 4 gives you the ability to supply about 1.9 amps split between the 4 pairs. The maximum allowed cable resistance for type 1 is 20 ohms, while the maximum allowed cable resistance for types 2, 3, and 4 are 12.5 ohms. Since the maximum allowed cable for 10100 and Gig E is 100 meters, this sets the minimum gauge of the copper wire required in the pair. I don't remember exactly what that is. I think on type 1, you can use a little bit lighter gauge cable. On types 2, 3, and 4, you typically use, I think it's 23 gauge cable to meet the resistance specification. But don't quote me on that. I'd have to go back and grab the books to take a look. One of the key things about power over Ethernet is safety. And the way that this works is the power sourcing equipment basically tests the load before sourcing power. And it looks to see if the pairs are open circuited or short circuited. If they're open circuited, it limits the applied voltage. I think the spec is 19 volts, but practically it's more like 12 volts. So that if you have bare open cable wires, you'll have a current limited, fairly safe low voltage on those wires. And if the cable is shorted for some reason, the power sourcing equipment will refuse to source power to the shorted cable. The powered device has to negotiate the current that it wants to consume before the power sourcing equipment will supply the negotiated current. And this is useful to prevent too many power devices being connected to a power source that might not be able to supply all of the current that they might need. So there's a power negotiating process used. The powered device, that's the load, puts a 19K to 26.5 K ohm signature resistance across the power pair to indicate that it is a power over Ethernet compatible device. And the power sourcing equipment measures that, A, to know that there's a PoE load, and B, to know that the cable is neither open nor shorted on those pair. Then a classification process begins. In the older method used in power over Ethernet, the powered device tells the power sourcing equipment how much current it needs by consuming a specific classification current at a relatively limited voltage. So the PSE will put a small voltage onto the line. The power device will put a current source or a current load across the pair. And I think there's 4 values of current that you can consume. This is used, sometimes some laptops have the capability to source power to power devices, and they particularly might not be able to supply much current because they're running off a battery, for example. And so for a couple of fairly low values of current up to 350 milliamps, this analog technique worked fairly well. It doesn't work very well for the newer power over Ethernet plus and power over Ethernet plus standards. And so the newer devices use the Ethernet Link Layer Discovery Protocol, or the LLDP, to do that. LLDP is a packet that is sent between Ethernet Layer 2 switching devices that are out of band to the data. So no computer actually sees these messages, but the Ethernet switches can communicate with each other and discover who their neighbors are. They can discover, for example, if they are in a bridge loop, and that's used by spanning tree to break up bridge loops, things like that. And so power over Ethernet plus and PoE plus added a new TLV or type length value packet to LLDP. And what happens is the power sourcing equipment powers up the PD at a very limited power. It's not a lot, enough so that the power device can then send back an LLDP TLV packet requesting a particular amount of current. The power sourcing equipment then responds with an LLDP TLV response packet specifying the maximum current that it will send. And once all that's agreed upon, then the power sourcing equipment will ramp up the current to the powered device. So it's fairly fail-safe, and it prevents damage under almost all practical cases. Some switches and routers integrate PoE and Midspan injectors. Everyone here has probably seen them. They've become very common. It gives you a much neater installation in that it eliminates requiring separate injector per cable onto the cables. In the old days, when we would hook up a 24-port switch with 24 Ethernet phones, we'd also need 24 power injectors. And this was a cabling nightmare in the closet. It was just a disaster. And so when you integrate the injector into the switch, you can just run a PoE cable direct to the powered device. If the end device on the switch is not a PoE device, then the switch knows that because there's no signature resistance, and it just doesn't bother to provide power to the load. And so that makes the switch very plug and play. A non-PoE device can be plugged in, the switch knows what to do. A PoE or PoE plus power device can be plugged in, and the switch, again, knows what to do. So you can plug in any kind of a device. Real common for a number of years were 8-port switches, where 4 of the ports were Ethernet only, regular ports, and 4 of the ports were power over Ethernet ports. I looked about 3 or 4 weeks ago. I couldn't find any of those on Amazon. Virtually all of the low-end switches are now 8-port PoE plus switches. And so all 8 ports are capable of providing PoE plus output. Now that for an 8-port switch is 240 watts if you consume about 30 watts of port, a little bit less at 25.5. And it means that you need a 240 watt power supply in that switch in addition to the switch consumption. And a lot of the switches do not have that large of a power supply. And so as you start plugging on PoE devices and they negotiate the power they want, the switch will stop supplying requested power once it runs out of power supply capacity, because it knows how much power it can source, and it knows how much it's already negotiated with the various loads. A higher end example is the switch on the bottom. This is the kind of router that I use in the home lab. And this is 24 ports of PoE plus and 4 ports of 10 gig E SFP. The 24 ports are power over Ethernet ports. And so if you, but the switch, the router only has a 500 watt power supply. The router itself consumes about 50 watts, and that leaves 450 watts of power available to those 24 ports. In this particular case, this router breaks it up into 3 groups of 8, and each group of 8 can source a maximum of 150 watts. And so it will negotiate the power by a group of 8. The switch does all this automatically. You don't need to configure or provision the switch. It will just know that how to keep track of the power on a group of 8. Again, these are only RJ45 Ethernet ports. The SFP plus ports, which are the 4 10 gig E ports on the bottom right, don't use a CAT cable, and so they do not provide power over Ethernet for those 10 gig ports. So it's just on the 1 gigabit Ethernet ports. Typically, however, you'll have a mix of load devices on a switch. You'll have some IP phones. You'll probably have some Wi-Fi access points. And so it's pretty unusual that you'll hit the maximum power per group when you plug on power to the switch. So in general, a 500 watt power supply is normally adequate for most practical use cases. This table comes from Wikipedia. Most folks use the 568B color code, and it outlines where the power goes and the signaling on the various pair. So for 10100 mode B, you put the pin 1 and pin 2 are the receive lines from the power sourcing equipment perspective. Those are the transmit lines for the end device perspective. So those will be used for data, and that's the DC positive 48 volt power rails. And the other pair, 3-6, is the DC return and is transmit as far as the PSE is concerned, or receive as far as the end device is concerned. And for gigabit mode B, you'll see that all 4 pairs are, in mode A and mode B, 2 pair, they use the opposite pairs, and power over Ethernet plus, all 4 pairs are, or PoE plus, excuse me, all 4 pairs are used for data. In PoE plus, just 2 pairs are used for data, and they can be mode A or mode B. So for references, there's a program called Get IEEE 802.3, and the IEEE 802.3 standard is available for free after it has been out for 6 months. So every time there is an amendment to the standard, once that amendment has been incorporated into the standard and the standard updated, once that updated standard's been available for 6 months, you can go at the link there and download that standard for free if you'd like. It's pretty unusual to be able to see a standard like this for free. Most of the standards require a cost. IEEE 802.3 has a public area for the working group, and that public area lists the additions to the standard that are currently in process, and that's at 802.3.org/3. Drafts for the in-process standards are not publicly available, and so there's a password protected private area on the web page as well. So to summarize it all, PoE has become very convenient. Having it integrated into switches is convenient. There's a lot of devices that are starting to use it. 4 pair power over Ethernet plus is not as common yet in switches and routers, because with the ability to source 50 to 70 watts, you'd need huge power supplies in those switches. So PoE plus is becoming probably the most common output available on switches and routers. The particular router that I showed in this diagram can actually detect, I think, the Ubiquity proprietary power, and it knows to source 24 volts on Ubiquity PoE output. And so it's got automatic mode switching. The network management on it will show that by LED color on the front panel what it's sourcing. And I believe it reports it also on the management interface, so that if you're remote, you can query remotely the PoE status of the router. You may not find that in an unmanaged Ethernet switch, but a managed Ethernet switch probably provides those management indicators for remote reading as well. And with it, that's the presentation. So back to you, Nathaniel.
Thank you so much, Tom. I really enjoyed that. Let's see, we'll open it up for general discussion.
Thanks, Tom. I think what it goes to show is, though, there's a lot of equipment out there that has common connectors, like the RJ45s, and you can no longer assume that because the plug fits, it's going to work.
Yeah, that particular router, it has a serial port on it, and the serial port uses an RJ45 on the router, and so you have to have an RJ45 to DB9 adapter to talk to the console interface. That's common on Cisco. I don't know about Juniper. MikroTik routers use that serial RJ45. So you're exactly right. Don't trust it.
Yeah, it's amazing how much complexity goes into it when you just plug the cable into the device.
So is there any gizmo I might want for my station that's that I might actually be able to?
Well, I use one. I have a Ubiquity 2.4 gig radio, and I have reflashed it to the Arden Ham network software. It's powered with power over Ethernet, and it's a 100 meg interface. So I just power that up, and the Ethernet cable runs up to the roof, powers up the radio, and I actually run a server that's attached to that network that provides a wiki and a bunch of other things. And that's all powered up over that PoE cable.
I wonder if there's some remote antenna tuners that would take advantage of that.
I don't know. It would be a very convenient way to do it for the antenna tuner manufacturer, because they can buy the chips for the power probably relatively inexpensively.
I'd imagine they'd have to do a lot of work on RF susceptibility and emissions both, because that with mismatched antennas and a high degree of tuning, that's always a cause for concern.
Yeah, I can testify that cables have to be carefully shielded. We're having interference problem on one of our repeaters, 2-meter repeater, that's picking up Ethernet over wireless that's up next to our antenna.
Yeah, there were a lot of problems with the 100 base T signaling, and it put out some spurs in the 2-meter band. I have not noticed nearly as many issues with gigabit Ethernet because of the signaling that they use, but shielded cables are always a good idea in an RF environment.
Yeah, unfortunately, the installer, the people who put it in, used shielded cable, but didn't ground the shield.
Yeah.
And now the weather has torn it apart.
Yeah,
shielded cable and lots of toroids.
Yeah, going to gigabit tends to disperse or spread out the signaling energy a lot, and it tends to be nowhere near as nasty.
Is there
Tom,
any,
that was great, and I apologize for being late. Are your slides available anywhere?
Yeah, they're on local radio club, k7mfr.org. And if you go to the reference page, you'll find the slides on there. K7 Mike Fox Radio, as in Medford, .org.
Thanks.
is there any provision if you wanted to limit the voltage? Say you couldn't handle 44 volts, but you wanted to limit it to say like 16?
Not within the standard.
Okay,
The cable losses there start to get really severe because the voltage drop at a particular current is a much higher percentage of the supply. And so you'd get a pretty limited voltage. So they tried to make it so that if there's nothing connected to the cable or you have bare wires and nothing's drawing current, that it shouldn't be hazardous.
because just thinking long-term for grape 2, the switch mode power supply will accept between 9 and 16 volts, but you take it above 16, the chip emits a flame for about 300 milliseconds.
It's just slightly shorter than the power sourcing equipment shutdown time.
Yeah.
Sounds like the voice of experience, John.
Yeah. Actually, I reversed it once with unlimited current, and the flame that shot out of a SOT-23 package surprised me. It's like, wow.
Yeah, that would shock me.
I would think the 48 volt switchers would be coming down in cost because they're used in so many places now that are power over Ethernet based. And so just the huge manufacturing volume ought to start to make both the sourcing and the load side more cost effective.
Yeah.
Well, it sounds like a lot of interesting applications and a lot of possibilities there. I know I have a Cisco IP phone on my desk right now, so I guess it's probably using that.
Mhm.
Depends on the date. The original phones are wired. The power polarity, I think, is backwards.
Yeah.
So it depends on the date.
Yeah, I don't know what date this one is.
I got a 7940 series. It's on the front label there, upper right corner. Which one do you have?
I have 7911.
Ah, okay.
Yeah, I don't know the models. I think there are a number of models out there now, of course. And so it's so convenient to have the injector built into the switch.
Mm-hmm.
It just really cleans up a real rat's nest of cables.
Mm-hmm. Yeah, I can imagine trying to put all of those power injectors in addition to this, which would really
Well, if you have 100 or 200 IP phones on the floor of a building,
mhm,
it could be a substantial mess.
definitely. Well, thank you so much, Tom. I really appreciate this.
You're welcome. I hope it was useful. Maybe some folks get ideas that, you know, if you can power up, if you can design equipment to be PoE powered, then folks don't have to fumble for a power source. They can just use their switch to power it. So it may, long-term perhaps, be more convenient for people.
Very good presentation. Thank you.
Could it also
Thank you.
could also possibly reduce some RFI caused by inexpensive switching wall wart power supplies?
Or make it worse.
That depends on the manufacturer of the switch.
Yeah, it could make it worse, right?
Yeah, it could be worse.
At least then you only have one device you have to go troubleshoot. That's great. Well, I guess we can open the floor for general discussion. I can also suggest some topics. Well, Well, one thing I do have an announcement. I had a research paper accepted yesterday. So I've been working on this paper for geophysical research letters for quite some time now. And for about the past year or so, I've been showing this same talk at all of the meetings of this traveling atmospheric disturbance. I finally got it written up and accepted. So they don't have the actual version up online yet, but I do have, this is the version, this is not the final version, this is pre-revisions, but it's very similar. There's you can get a preprint in the chat. So it's slightly different from the final version. They made us redo the processing on the GPS TEC data to get rid of some artifacts. And one reviewer actually wanted me to rewrite the abstract and the summary to really emphasize the fact that the amateur radio was the new thing here, using amateur radio to look at these TIDs. So they really had me re-emphasize that in the new version. So hopefully next week or the next time we meet, I'll have the final accepted version out, or I can post it on the listserv when it comes out. So the next step is there will be an accepted version that's posted online, and then they send me a proof, and I have to go through and proof all of the manuscript, and then they put the final version online. So
Congratulations.
thank you. So it was very exciting.
Yeah, I mean, it's interesting that a 100-year-old technology, if you want to call that, of amateur radio is so much in the forefront of that. So that's great.
Yeah. Well, it's really cool. I think what's really made this possible in a lot of ways is RBN and WhisperNet and PSK Reporter and all these software-defined radios and computers and all the networking that lets us get all the information, lets us observe everything, record it, get it all into one place, and then we have now the software tools to be able to analyze it and visualize it. Because if you look, I can open this up. Actually, what I'll do is I will open up I can get the actual accepted version up. Overleaf. If I go, it's recompiling. Should be ready in a minute. Great. So yeah, here is the accepted version. And yeah, you just have to put so much information together just to generate this one figure from all of these different stations, transmitters, and receivers. Just getting it all together and getting it visualized in the right way to be able to show this. And then same thing with the GPS receivers. So we compared what the ham radio saw with what GPS receivers around the country observed. And we were able to see that when the GPSs observed an increase, go down here. Here you go. When this white line is a median value of the total electron content measured by the GPS system over the United States, and this red line is a trace of the bottom of the skip distance measured by ham radio, you can see an inverse relationship, so that when the total electron content decreases, the range on 14 megahertz extends and vice versa.
Yeah, so that would make sense. It would say that as the total electron content decreases, the ionosphere is less heavily ionized.
Mm-hmm.
And so the skip distance is further out as a result. So intuitively, it would make sense.
Yep. That's exactly right. And the other thing that was interesting, and I haven't shown this at any of the meetings yet. So I took the RBN data, it's RBN Whisper and PSK reporter. I put it all together. So all the ham radio data I put together, and then I took little slices of it. So there's a slice here. This is at 41.5 degrees north. And then I moved it down, a degree each time. So going from north to south. And if you, really zoom in and saturate the color bar, you can see the wave here. And I have a red arrow pointed to where the top of the wave is. And you can see there's a phase progression. And as you go from north to south, it looks like it is, in fact, progressing from north to south. Except over here, it seems to go backwards. But there's a lot of possibilities why that might be. But at least for the top three, we were able to show a coherent wave progression. And and if you use this to estimate the velocity of the wave progression here, it matches what the GPS wave velocity as well, very nicely. And the final thing, what we believe caused it, is this is the supermag electrojet index, which is similar to the auroral electrojet index. So you saw the aurora kick up a few hours before we see the TID down here. And if you look at how long it takes, if you use the estimated direction of travel and the velocities we measure from this data and project backwards, it takes you to about this time and location. So, yeah. So I guess, let's see. So Steve, I know Steve's been working on some things, and Jim has been working on some things with the Tonga. Does anyone want to talk about the Tonga event at all?
Not really ready to say much more, except that I have seen some evidence in the pressure and some other indications that propagate around the Earth, and they seem to correlate pretty well with when we see some things happening in the ionosphere. Now, saying there's a cause and effect there, I'm not quite there yet.
Yeah, that makes sense. I think in the next couple weeks, we'll be seeing some peer-reviewed papers come out. So it'll be interesting to see what they say. And it would be nice if, maybe we can look at what you have again some more in a couple weeks from now.
I'll try to have it in some kind of decent form by then.
That'd be really nice. And then Steve, you've been making measurements, right?
I have. I was kind of intrigued with and wondering how the heck a solar flare could bring down a bunch of satellites. And then I watched a video that space weather woman Tamitha put on, and she explained it very well.
And she'll be at the HamSCI workshop in person.
That's cool. So what she said was that it was a 1-2 punch. There was one solar flare with a CME. Solar wind arrived with a polarity, call it north. And that combined with the Earth's magnetic field and got the ionized atmosphere rotating in one direction. It slammed into the neutral atmosphere, drug it along with it. And that spun up and established momentum in a rotational effect on the atmosphere. And then the second flare happened and the other CME came in with the opposite polarity, which started it moving the ionized atmosphere the opposite direction, slamming into the neutral atmosphere, trying to make it go the opposite direction. You get the idea, a lot of friction going on, gigawatts of power. And that heated the atmosphere, caused it to swell at just the time that the Skylink satellites were leaving the perigee of their insertion into the low Earth orbit. added enough drag to slow them down. And 40 out of 49 re-entered and burned up.
Is that paper on her website, you know, or?
It
where
was
do you-
a YouTube video.
Okay,
And you know, I asked a guy about that, and he said the same thing happened in the 80s with Skylab. That's what brought Skylab down, swelling of the atmosphere. So anyway, after that happened, I'd been monitoring 10 megahertz spectrograms on WWV anyway, and golly, there was a lot of turbulence. I haven't done much monitoring of 10. And what I did was a few years ago, and we're up on the sunspot cycle now. So it's a totally different ionosphere. So it's hard to tell whether or not all this turbulence I've seen, which is like plus or minus a full hertz to hertz and a half, I mean 2 to 3 hertz peak to peak swings, is still settling out from this upset that we had, or whether this is just part of the coming up on this new sunspot cycle.
you know,
So-
that's interesting. I've noticed the same thing, a lot of turbulence recently.
Good. Well, that's what we should compare notes. And David is taking some 15 megahertz data. And gosh, my mind just went blank. Who did you ask me to contact, Nathaniel? And I did.
Bill Engelke.
Bill, yeah, Bill. I sent Bill an email. I know he's having surgery today.
Yeah.
So I haven't heard back from him, but maybe we should compile this stuff.
Mhm.
See if there's some sort of a correlation with those flares and the CMEs.
I agree with that. I think so you weren't on in the morning discussion, Steve, but in the GRAPE group in the morning, we've started doing some data analysis tutorials where we're actually opening up the GRAPE files and actually starting to look at the data. And I've been showing people how to do this in the IPython notebooks. So I think as we make some progress in doing that, we can probably look at some of these case studies and try to aggregate the different data sets together and maybe get people trained up on how to really analyze this and put it all together.
Well, there could be some cool comparisons here. The Tonga event was a very localized source. It started right here, and that pressure wave propagated out away from that epicenter. The mechanism that brought down the satellites was global.
Mm-hmm.
And so it makes sense that what you would see would be turbulence, because you're mixing, you know, you have rotation in one direction, Tamitha called it the flywheel effect. And then opposite polarity tried to reverse that. So you have wind going both ways, and that makes turbulence, which is what we're seeing. So another good question, is it actual physical motion, or is it, you know, I don't think it's physical motion when we see a frequency positive swing in the morning and a negative swing in the evening. I think that's not vertical winds. I think that's just the parts of the ionosphere that either get ionized or recombine. In other words, the atoms are staying still, but the ones that are ionized or not ionized is what's changing. But this other effect might be actual physical motion, simply because of the stirring effect.
Yeah, the stirring. I haven't thought of it that way. I found Tamitha's her video, and I put the link to it in the YouTube
Okay.
chat there. So anyone who wants to
Yeah,
see
next
what-
time I have an hour and a half to spare, I'll look at it.
Yeah, it's a long video.
Yeah.
Yeah, that's quite a video. Yeah. Yeah, I think there'll be some really interesting things to look at. Well, I think I'm gonna say
You can speed up YouTube videos, by the way, and run through the parts that sounds a little Donald Duckish when you get up to 1.5 times normal speed, but
yeah.
it does make it possible to get through and concentrate on the interesting stuff.
You know, you can do some movies that way too. And for a while, Radio Shack sold a tape recorder that would let you play it back at 3x speed but they would translate the frequencies down so it didn't sound like Donald Duck.
Hmm.
It was just somebody talking very, very fast, but you could understand it. Your brain could actually follow it.
That's really cool.
My company actually pioneered that. I was
Really?
working on the synclavier, and we had time adjustment. You could pitch shift, but you could also time shift. They used it a lot for fitting things to 30-second advertisements.
Yes. The lawyer speak, you hear a lot that way.
That's right.
Well, that brings us to the top of the hour. So thank you everyone for joining us. Thank you to our presenter, Tom. It was great seeing everyone. And the in-person registration for the HamSCI workshop is open. So if you are planning on going in person, please register there. If you are going to attend virtually, that will be available toward the end of the month, at the beginning of March, when that link becomes available to me. So thank you so much, everyone. I hope you have a great day.
Thank
Great.
you.
Stay well.
Thanks, Tom.
Good day.
Thank you.
7-3, everybody.
1-3.